Так, ну, Брюс выступает, он расскажет про лог-менеджер, загадочный лог-менеджер Postgres. После Брюса следующий будет доклад про очень интересную архитектуру глобальной системы хранения персональных данных.
We will start with Bruce Momjian presentation, and then we will talk about the storage of information by Pavel Konotopov. Right now, Bruce Momjian. Unlocking of logs.
It is wonderful to be here again in Russia. I apologize that I was not able to come last year, but this year Ivan and I have some big plans, so I will be here a lot more often. Hopefully, I always love coming to Russia. I will be visiting Tyumen and Tver during this trip, so 2 new cities for me. Very exciting. My name is Bruce Momjian. I am one of the Postgres core team members. I am also an employee at Enterprise DB, and I've been working with Postgres for 23 years now. I live in Philadelphia in the United States. I travel about 90 days a year and go to about 40 conferences. My website, which is listed right here, has the slides for this talk. So if you'd like to look at the slides later, they'll be on the website of the conference. They're also on my personal website. There are about 30 other presentations on that website, as well as videos of those presentations, and over 500 blog entries. So it's a big resource if you like this type of material. I was a high school teacher and professor before I started with Postgres, so I'm used to doing this. I am very excited to be giving this talk. It is one of my more interesting talks. It is also probably one of the ones that has the most slides. So there are 110 slides in this talk, which means I may not have time for questions. But what that also means is the talk starts very simply, and then it gets harder and harder and harder. Toward the end, it'll be pretty complicated. So if you think the beginning is boring, I am sorry. But by the end, I believe you will find that it is clear. And I also want to thank our translators for allowing those who are not as fluent in English to understand me. I enjoyed their translation of Ivan and Oleg's talk earlier. So, what is this talk? This talk is kind of unpleasant. Locking is not a very popular topic. It's kind of a thing we would wish would go away. But just like going to the dentist, locking is something that is an issue for most people who are running concurrent systems, not just databases, but anything that has concurrent activity is going to need some type of locking. So what this talk attempts to do is to give you a very basic introduction to locking. Then we talk about something called transaction identifiers. It's a fairly boring part of the talk, honestly, but you have to understand them. Then we go through lock types, which is fairly mechanical. We'll explain all the different lock types in Postgres. And finally, we'll finish talking about some locking examples, and that's where it gets really complicated, all right? So again, I will be moving quickly through the talk because there are so many slides, but I believe it is pretty clear and easy to understand. And again, I'm very thankful for everyone for having me here to speak. I am looking forward to the rest of the conference. So let's talk about locking. Locking terminology is fairly complicated. How many people know what this is from? 1. Wow. Okay, I am very old then. This is from a game called, I have 2, thank you. This is from a game called Adventure, which was a text-based computer game back in the 80s, 80s, I think. It's technically called Colossal Cave Adventure. So if you're curious, again, the URL there at the bottom. You would get into a cave, and you got into this text, and the text would change, but it almost read the same all the time. That's how I remember it. And frankly, that's the way I feel about the locking names. I believe these locking names that Postgres used came from Oracle, and we have used them. Frankly, I would love to have come up with some better names, but we could not think of any. So when I hear the terms, I am often confused. Well, there's share update exclusive, and then there's share row exclusive, and then there's access exclusive and row share, right? You can see it isn't very clear. We can sort of break it up. Some of them have the word share in it. Some of them have the word exclusive in it. One of them has both in it, okay? So I will be showing you to start some examples of exactly how these locks are instituted. And of course, also the word access and the word row is interchangeably used. We have access share, row share. Fortunately, we don't have any access row, together. That's good. Another issue that you need to understand in Postgres, and something I'm not going to be able to cover in this talk, is something called MVCC. I do have a very popular MVCC talk on my website. If you think this is complicated, the MVCC talk is perhaps my most complicated talk. But again, there's a video, you can go through the slides. If you're interested in how Postgres does multi-version concurrency control, then I encourage you to read that presentation. So, another housekeeping thing that we need to understand is something called transaction IDs. Most databases cannot run without some type of unique identifier that explains what a transaction is. We number them. In Postgres, we actually have two systems of numbering transactions. Yeah, I know, not really pretty. Another thing to keep in mind, these slides are going to be fairly complicated, so keep an eye, whatever's red on the screen, that's probably what you should look at. So for example, right there, what's red? The transaction ID number. Okay, so that's kind of where you want to look on that slide. What I'm doing here is I'm calling a function called select PG backend PID up at the top, and it's returning my transaction ID. Another thing, if you like this presentation and you want to run it on your own database, you can go to this URL in pink and download the SQL for this presentation. And you run it right in PSQL. You just pipe it into PSQL. The entire presentation will just shoot down on your screen. It will not be in color, but you will be able to see it. Okay, so that's what that SQL file is for. So there, in this case, is a transaction ID. It turns out that's the number we've been assigned. Okay? There's a second type of transaction ID in Postgres called a virtual transaction ID. And we have to understand this, or we can't really understand the locking behavior of Postgres. A virtual transaction ID is a transaction ID that does not have any permanence. So for example, if I issue a select command, I'm probably not going to be modifying the database. I'm not going to be locking anything. So when you issue a simple select, we do not give you a permanent transaction ID. We merely give you a virtual transaction ID. And this improves Postgres performance. It improves the ability for cleanup, reduces cleanup problems. So the virtual transaction ID is made up of two numbers. The first number before the slash, to the left of the slash, is the backend ID, and the right is just a counter. So for example, if I run that query there, it tells me my backend ID is 2. And if I run a series of select statements, you can see that my virtual transaction ID is getting one larger every time I run a query. So again, 2/10, 2/11, 2/12. Okay? But keep in mind that, notice I have two columns here. On the left is my virtual transaction ID, 2/12. And on the right, my permanent transaction ID in this case is blank. Because up until this point, this transaction has not modified the database. Therefore, I have not been assigned a permanent transaction ID. As soon as I run the analyze command, the same query now gives me a permanent transaction ID. Okay? So notice how that changed. Before I didn't have one, now I do. All right? Now I can see that just asking, here's another query, another transaction here at the top. My virtual transaction ID is 2/13. If I merely ask for a permanent transaction ID, I'm assigned one. And then when I run the query, I get one. So again, there's this permanent transaction ID, there's a virtual transaction ID. Just understand that's part of the way Postgres behaves. Okay. So section 3, we're doing really well. This is the part where we just go through the various lock types of Postgres. Not super exciting. Again, the super exciting part to me is the last section. But again, we have to lay the groundwork so the last section makes sense, because if we don't, it's going to be very confusing. Okay? So what we're going to do is we're going to go through this section, and we're just going to look at each of the lock types, and we're going to show you examples of how they're set up. And I'll also show you some queries that we can use to see locking in Postgres. Okay? So, to create a query to see what's happening in Postgres, we need to issue a statement on a system view. The system view in this case, in red, is PG locks, right? PG locks is our system table. It tells us what locks currently are being held by Postgres. However, it's too hard for me to show you PG locks alone because it's kind of complicated. So what I did was I created a view that shows me PG locks, and it does some work for me to make it easier to understand. It excludes my own lock and my own batch session and so forth. Okay? Again, this is just standard SQL, but it makes it easier to show you what's going on. In fact, another problem is this view is too wide. So I had to create a second view which shows me the first couple columns of the system table, and then another view which shows me the last couple columns of the system table. Again, this is very complicated, so I'm trying to make it kind of simple. Okay? Again, these are all on the PDF. They're in the SQL file that I gave you, so feel free to use that for my website. Okay. So we're going to create a table called lock demo, and we're going to put one row in it. This is our sample table we're going to use through this section to effectively create just examples of locking. Okay, so one row and one column. Okay, so our first type of lock is called access share. Access share is our least restrictive lock, meaning that it doesn't really conflict with almost any other lock. So what we can do, if we want to explicitly define the lock, we can actually issue a lock table command. That would be explicit because we're doing it visibly. Okay? We could say lock table lock demo in access share mode. Okay? And if I run PSQL in the background, again, if you don't understand that, that's okay. All I'm doing is I'm running a second session from within my first session so I can see what the output is. So what I'm doing here is I'm going into another session and I'm saying, show me the lock view for this particular query. And you can see I have an access share lock on that table, which is exactly what I asked for. And it tells me the lock has been granted. That's what that true is, that T. And it tells me it's on the lock demo table. Very, very simple. Okay? Now, and also the second column here, the second part of the table, there's nothing there. It's all blank, pretty much. So I don't usually show this table unless I need to. But anyway. So if I issue a select command, this is an implicit way of me asking for an access share lock. So I just select on my table, and I run a query, and my query returns a set of rows, one row, which just says, yeah, you just got an access share lock. So a select causes an access share lock on the table. And that doesn't conflict with very much. Again, it's a very low-level lock. Okay? What if I do a select and I name 3 different tables in the select? Remember, before I just issued one table, right? Now I do 3. PG class, PG namespace, PG attribute, okay? And when I now look at the query, I now have, wow, I must have, what, 8, 9 access share locks on 3 tables. Why? Well, in blue, you can see the 3 tables, PG attribute, PG class, and PG namespace. But you can also see that all of the indexes that are defined for those tables also have access share locks. Okay? These are, again, very low conflicting locks. All they really do is to prevent somebody from dropping the table while you're selecting it. Makes sense, right? You may select data that goes away while you're selecting it. That's not a good thing. So we have this very low-level lock called access share, which just says, don't delete it while I'm here. And that effectively is what it does. Okay? That's kind of odd. Okay. Row share. A row share lock is a little different. Just explicitly, you can say for row share. Okay? An example of that would be a select for share. I'm not sure how many of you use share locks, but it's a way of locking individual rows so that nobody deletes them or modifies them while I'm viewing them. Okay? So that's what the share lock does. You can see our current transaction ID is 681 for the select. And this is interesting. So what it's done, and this is the first time we've seen a number over here in the lock field, is it's taken my own transaction ID and it said, I am locking it in exclusive mode with the transaction ID. All right? So all it's doing is it's saying, I have a row that's technically locked somewhere in that table. It doesn't tell me where the row is, it just tells me it's right there. The second row, so we'll get into more detail later, but this is something we'll see a couple times where you actually lock yourself. You say, I'm locking it and I own that lock right there. Okay? Row exclusive lock, again, explicit, say row exclusive. Or if you delete a row. If you delete a row, we're going to ask for a row exclusive lock on that table. As you can see, that's exactly what happens. All right? Share update exclusive, this is one of the longer ones. Again, big long word there. That would be an analyze command. Share update exclusive would be used by analyze. A share lock, again, you can explicitly lock it in share mode. Or if you create a unique index, you can see there's a share lock right there. That's part of it, and in fact, it's locking the table. It hasn't created the index yet, it's just putting a share lock on the table. And by default, a share lock on the table means that other people can read from the table, but nobody can modify it. And that's what happens when you create a unique index. Okay? Now, if I had done create unique index concurrently, I would have a different type of lock. Because as you may remember, the use of concurrently in create index reduces the locking requirements. But I didn't do that. I made a normal lock, normal index, and therefore I'm preventing writes to the table while this index is being created, okay? If I had used concurrently, I would have a different type of lock, all right? Share row exclusive, again, we can do it explicitly, or we can create a rule. This happens to be the only case we use this lock for, okay? Exclusive lock, an exclusive lock is not automatically done by anyone, but again, you can explicitly do it if you wish. Okay, again, this is all just showing you all the lock types. Access exclusive is the default mode for the lock command. It's also if you do a cluster on the table, it would do an access exclusive, meaning that nobody can read it or write it, or nobody can write it. Also notice it's locking the indexes as well, not only the table, but it's locking the indexes, okay? This is the second page of our access exclusive lock. You can see exactly what it's locking in the PG type table. It's actually locking individual rows in the table. It's kind of interesting. Okay, so again, that is all the background I wanted to give you. What have we talked about? We talked about locking terms, we talked about transaction IDs, we talked about virtual transaction IDs and permanent ones. We went over the different lock types and I showed you the views, okay? Now what we're going to do is we're going to walk through a whole bunch of locking examples. This is the most interesting part. Having gone through sort of the background, we're gonna look at a whole bunch of very interesting cases, and my goal in this talk is for you to have a better understanding of exactly what Postgres is doing when it's trying to lock things. It's trying to lock things as minimally as possible. And again, I think it does a very good job of that. But let's look at some specific examples. Okay. So we're going to start out with our table, one row, and there's a 1 in there, okay? And you notice when I do an insert, I get an access exclusive lock on my own transaction ID, and I get a row exclusive lock on the table, okay? Now, what if I insert 2 other rows? So now the table has 3 rows. So I inserted 1 row and I got this output, all right? And I insert 2 more rows. What's strange about that? Well, it's strange because I have 3 rows added to this table, but I still only have 2 rows in the lock table, right? And this is a fundamental behavior of Postgres. A lot of people think that in a database, when you lock 100 rows, we should have to create 100 lock entries, right? If I lock 1,000 rows, I should have 1,000 lock entries. If I lock 1,000,000 rows or 1,000,000,000 rows, I should have 1,000,000 or 1,000,000,000 lock entries. You know, that doesn't work very well. If you've used a system that creates lock entries for every single row, the behavior is poor. You have to define the lock table. The lock table can overflow, and then the transaction aborts. I used to work on a database that had that kind of behavior. Postgres does not do that. So one of the things about this slide is it really clearly illustrates to me that we're not, there's another system working inside of MVCC that's locking the individual rows. These are more sort of table level information. All right, so when you lock 1,000,000,000 rows in Postgres, Postgres is not creating 1,000,000,000 lock table entries. All right, and this is again really good for performance. Right? What about an update? So I'm going to update the row to itself, and you can notice that it actually has done 2 different things here. It's locked the table, but it's also locked the index. And the reason it had to lock the index is because there's a unique constraint on this table, and we wanted to make sure that nobody changed it, so we locked both of them, okay? What if I update 2 rows? Well, again, same behavior. I just did 3 updates, but I have the exact same number of lock table entries. If you're curious how Postgres does do that locking, you have to look at my MVCC talk to see how Postgres internally marks the rows that have changed. Okay, so there is a way that Postgres does it, but it doesn't do it in the lock table. It does it at a much lower level and a much more efficient level. What about a delete? I'm going to delete row 1. I have my 2 lock entries. And if I delete all the rows, I still have 2 lock entries. So again, the idea is that whether I insert 1,000 rows, update 1,000 rows, or delete 1,000 rows, the individual rows that I am updating or changing or deleting are not being recorded here. They're recorded as a lower level inside the row itself. And the MVCC talk talks about that. But again, it's important when you're analyzing locking to understand that you have a lock at the table level, but individual rows are not appearing at all here. They're not recorded at this level. Okay? What about an explicit lock? Again, I do a select for update, okay? And I have 2 lock rows, and I do select for update on all of them, and I still have 2 lock rows. Again, same thing. We're not creating individual records for individual rows because that performance is poor. It can overflow, not the way we want to go. Okay? For share, same thing. Do all 1, do all 3, it's the same. Okay. So let's go back, restore the table, delete all the rows, put 1 row in again. Okay. So another behavior that you're going to see in Postgres, and this is a well-known, very desired behavior, is that you can be doing updates and selects on the table at the same time. And the selects do not block the updates, and the updates do not block the selects. This is a behavior of multi-version concurrency control. We normally say readers don't block writers and writers don't block readers. That's the way we normally explain it. And I'm going to show you an example of that. So what I'm going to do is I'm going to actually do a select, and I'm going to look actually. We did the insert, and you can actually see 694. You can actually see the transaction ID that did that insert. Okay, this is an idea of how it works. Okay, and now if I look at my backend ID, it's now 695. And I can actually look, and I can see that 695 is actually appearing in my table. And now if I do an update like this, here at the bottom, I get a different case, okay? So in this case, 695 has an exclusive lock and an access share lock. And again, the update has the same behavior, but there's no conflict between the two. All right, which is kind of unusual. Notice the top one is an access share lock, the other one, bottom one is an access exclusive lock, but in fact both transactions went through. And again, you're going to have to look at my MVCC talk to really understand what's going on. But this is an illustration that you can do stuff at the same time, selects and updates at the same time. Okay, let's reset and start again. If you try and run 2 updates on the same row, it will block, right? Remember I said readers don't block writers, writers don't block readers, but writers block other writers, right? We have to do that. We can't have 2 people updating the same row until the one finishes or aborts or commits. That's just fundamental. We can't do any better. So I'm going to actually illustrate this here. I'm going to look at the lock demo table. We have 1 row, and it's transaction 698. We're going to update that to 2, and we're going to see now the row is 2. We have a backend ID of 11306. Our transaction ID is 699. And what we see here, this is the first time we're really seeing something interesting in the table. 699 is the first update, and it succeeded, or it's pending transaction, pending commit or abort. The second one take a look at the numbers here. See 2/51? That's the first query. That's the first session. That's the one that made 1 to 2. 3/112? That's the second query. That's the one up here at the top that set the value to 3. Okay? And what you notice is that the top one has locked itself, which is 699, but 3/112, it has not been granted a lock. That column in the center that says granted, you know that's a false. Means it's waiting. And what is it waiting on? 699. Okay? So if you take a look, 699, where is that? That's right up there. Okay? So what the first session's done is it's actually created an exclusive lock on its own transaction ID. That's the way Postgres does things. It locks its own transaction ID. And then if anyone wants to wait on it to commit or abort, it effectively has somebody wait on its own, on the transaction ID that it's waiting for. Okay? So that's why that weird line at the top. Let's look at that a little more clearly. On the left, 11306, that's our permanent transaction ID. We know that. Oh, I'm sorry, that's our process ID. I'm sorry, not a transaction ID. That's our process ID. Second column, that's our virtual transaction ID. We talked about that. Third column, lock type. What does that mean? Well, that's a weird entry because it says it's locking a transaction ID. That's what it actually is doing. Notice the rows underneath it all say relation. You see that? So there's two types of locks in the table. There's relation locks, which have relation names on the right-hand side. And then there's also transaction ID locks, where you're either locking yourself, which is what's happening on the first row, or at the bottom row, a transaction ID lock that we're waiting on. We're waiting on 699 to finish. Okay, so when I look at this output, you're looking at two types of things going on. You're looking at transaction ID locks. The first row, it's locking itself, waiting for it to finish. It locks itself to sort of create a fake lock that other people can wait on, effectively like a placeholder. This row here in the middle, and unfortunately I can't point at it, but this transaction ID, row 5 or 6, that's the same entry as the top one. So transaction 699 locks itself, transaction 700 locks itself, and down here at the bottom, we have us waiting on 699 to finish, okay? And you can actually see in the tuple lock, you can see the exact number it's waiting on. You probably didn't notice it, but back here, notice that says 0/10, right? That's the page number and the offset of that particular row. And in fact, we see that number, that becomes 0/11, okay, when we update it here. But notice that we actually have 0/10. It's actually waiting on. We actually can see which row it's waiting on. We can't see all the locks. Remember we talked about we don't have that, but we do have the ability to kind of look and see, okay, that's the row that I'm waiting to commit, okay? Once the update finishes, this is what we get again, okay? Transaction 700 is now the only locker, and it's not waiting on anyone anymore because it's committed. It's finished. It's kind of waiting for its transaction to finish. So as soon as 699 finished, everything cleared up. It went away. We're not waiting on 699 anymore. And transaction 700 is actually saying, I'm good. I've got all the locks I need. I have true in all of my granted columns. Okay? As if things were not complicated enough, we're going to create another view, which actually gives us a hierarchy. I don't expect you to understand this query, but it is going to give us a clearer view of what's happening. Again, it's in the SQL file. Okay, and this is a recursive view, which again has another section, and then it kind of brings everything together. So let's use that. What if we do 3 concurrent updates? So the row currently is 3, we're going to change 3 to 4, and there's 4, okay? Transaction ID 702, right there. And now I'm going to set 4 to 5, 5 to 6, 6 to 7. Okay, so I got a 4 in there. I'm going to say, just update it to 5, and then update it to 6, and then update it to 7. So I'm queuing up a whole bunch of people who are going to be waiting for this one transaction to finish. And if you look, it actually now makes sense. Okay? What is the first row? First row is 702. That was the row, that was the transaction ID that originally set this value. What do I have in the granted column? I have 3 false granted rows. Those are my 3 updates, 5, 6, and 7, which cannot be committed because we do not have, we're waiting on 702 to finish. In fact, look at the first one. You see the first F? It says I'm waiting on 702. Where's 702? Up at the top. Transaction ID lock. Right? Remember, see, take a look over here. 1 transaction ID lock, 2 transaction ID, 3, 4, 5 transaction ID type locks right there. Okay? And if you look at the other not granted 704 and 705, they don't say anything here because they have no idea what's happening. They're like, I don't know what's going on. I'm just going to go to sleep because I'm behind somebody else who's already waiting. So if somebody else is already waiting, I'm just going to like sit there and somebody will wake me up when I have a chance to change that row. And that's exactly what it looks like. Very clearly, they're all waiting on the 12th entry in page 0. Okay, which is, I'll back up. This is exactly what we saw right up there, right there, 012. Okay? Now, as soon as the first transaction commits, then, you can kind of see the hierarchy going on. Now everything's clear. They're all kind of clean. They're still waiting, okay? So then, let's see here. So here's what happens. So 702 commits, and what happens? 703 now gets the row lock. And now 704 is waiting on 703. No, I'm sorry, 704 is waiting on 703. 705 is waiting on 703. Okay? And then, once they finally finish, they all kind of clear themselves out. So what I'm trying to point out is things queue up. They get into it's like a traffic jam, basically. The first car stops. Everyone piles behind them. That car moves. Then the next car can get the lock and then move forward. Okay? Now, if that wasn't complicated enough, we're going to talk about deadlocks. Now, I'm not sure how many of you have dealt with deadlocks before. It's a fairly common problem in database systems. But a deadlock specifically is a case where one session is waiting for some other session to do something, and the other session is waiting for the first session to do something. So if I'm with Yvonne, and he says, give me something, and I say, no, I'll only give you that if you give me some other thing, and he says, no, I won't give it to you unless you give me, then we're at a deadlock, right? I'm sure Yvonne would not do that, but you get the point, that 2 people want things, and they won't give it up unless the other person gives it to them first, and there's no solution to that. So effectively, the database has to detect that and then terminate or cancel one of the sessions. Because if not, they'll sit there forever. All right? This is common not only in databases, you see it in operating systems. Any concurrent environment potentially can have deadlocks. So let's start with a simple deadlock case. We're going to put 2 rows in the table, a 50 and an 80. Okay? I don't know why I picked those numbers, just whatever. So, first row, I'm going to update 50 to 50, and I'm going to transaction ID is 710. Then I'm going to change 80 to 81 and 50 to 51. All right? So that's what it's going to look like. So 710 has the row lock. 711 is waiting on 710. Okay, we saw this with the update case, right? We've got 710, which is our owner of the row, and 711, and 711 is waiting for 710 to finish. And we even tells us what row it is that they're deadlocking on. Okay, but here's where it goes weird. We actually now update 80 to 80, and here's where our deadlock is. So 710 is waiting on 711, and 711 is waiting on 710, right? This is not going to end well. There's no way to get out of this. They're going to be waiting for each other, and therefore it's going to stall. So because we don't want that, Postgres has, and most databases have some way of detecting when this happens. And when this happens, you can see exactly the rows they're waiting on. You get this type of error. And it's very clear. It says that process was waiting for a share lock on 711, blocked by that process. That process was waiting for a share lock on that transaction ID and was blocked by that process, okay? And as you notice, 11.608 is the same as here, and 11.642 is the same as there. That's our deadlock, okay? What about a three-way deadlock? Is that possible? Yes, indeed, it is. So we put 40, 60, and 80 in the table. We change 40 to 40. We get a lock on it. We change 60 to 61, 80 to 81, and then we change 80 to 80, and bam. 714 is waiting on 716, 715 is waiting on 714, 716 is waiting on 715. There's no way around this. It's not two people, it's now three people. I want something from you, they want something from a third person wants something from me, and we're all gonna wait for the other person to finish. And Postgres, as you can see, knows what row that is, and it will effectively issue this message, which indicates that we have a problem where three are blocked together. There's no limit to how many Postgres will detect. If it's 20, we'll detect it, okay? Another example here, serializable. If you've ever used serializable transactions, there is a special serializable lock type. Back in number 719, here we go. 719 actually has pretty normal output. If we say set transaction level serializable, and we run that 720 now, you can understand that we now have a different type of lock. SI stands for serializable. So we have a new lock type called SI read lock, which effectively is a serializable type of lock, which allows for serialization. Another example is insert unique. We have a unique index on this table. So if I insert the value 2, I can see, and now I insert the value 2 again. So I have a 2, and up here at the top I'm inserting another 2, right? So what you can see is 721 owns, it looks pretty normal. Okay, it's got a row exclusive lock on lock demo, but 722 is now waiting, and notice it's locked the index and it's waiting for 721 to finish because it can't put the 2 in until it knows what happens to 721. Okay. Again, once if we do sub-transactions, another case, 723, if we do a save point, and we update it again, you can see we now have a new transaction ID. This is another behavior that you should be aware of. When I roll it back, the transaction ID goes away, 724 goes away, but now I have 725. So again, what I'm trying to do here is show you just examples of some unusual lock types that you may find in the lock table, whether it's serializable, whether it's save points. These are different lock types that will appear in the lock table. A third type is called advisory locks. This is a way of creating explicit locking in Postgres with a function called PG advisory lock. And you can see the lock type specifically is listed as advisory here. Okay? And you can see it says advisory right there, and you can unlock it at the same time with the PG advisory unlock. Okay? Wrapping up, I wanted to show you one final crazy thing. I'm going to create another view, but I'm going to join the PG locks table to the PG stat activity table. Why would I do that? Well, this is going to allow me to see all of the running sessions and what locks it's waiting on. Kind of interesting, kind of bringing the query list and the locking list together to see what's going on. So we create a view, PG stat view. We update the row to 1, it's 724, and we now update the row to 3. And now what you can see here is the query, right? The whole query is listed right here on the left-hand side. And now on the right-hand side, I can see the locks and what's created by them. So that might be much clearer to you, so you don't have to kind of look back to see, oh, what session is that? What's it doing? Do I have to join it? This is kind of doing it for us. Another function, incredibly useful, PG blocking PIDs. You probably never heard of that before, but what it effectively does is it allows us to say, for that session, 11740, what process ID is it waiting on? Okay? And you can kind of see, if I'm looking at 11740, which is somewhere in the middle there, and I know it's hard to see because of the line, but there's an F up there. You see like row 6? And you can see it's waiting on 724. 724 is up at the top. 11306, in fact, is the number. So what that function's doing is it's walking through the lock table. You catching this? I know it's really complicated, but it's walking, that function is walking through this lock table, and it's saying, oh, for that process ID, where's my false granted? What XID lock is it waiting on? And then it goes up and it says, what's the process ID that goes there? So if you're curious what something's waiting on, you can really just run PG stat activity and just query this blocking PID for your process ID. Incredibly useful. We only added, I think, in 9.6, so it's like 5 years old, but really, really useful. Again, same thing on the second query, shows exactly what we want to see. So that is what I wanted to cover today, as I suspected we would use all the time because there's so many slides. Again, the slides are available right there on the right-hand side. I will be around certainly to answer any questions. I'll be here for obviously until Thursday. So if you'd like to ask questions, I'd be glad to do that. But again, we are out of time, so I want to thank you for attending, and I'm sure you'll enjoy the rest of the conference. Thank you.
Вопросики?
Any questions?
Кто хочет спросить про локи?
Who wants to ask about locks? Into the microphone, please.
For example, if I try to update one rows and second session try to delete table, as far as I know, it should be something like intent lock. Is it in Postgres intent lock?
So I'm going to answer that by going way back. So you might remember whenever you do anything, where is it here? Yeah. So whenever you do a select, okay, what we do is we issue an access share lock. And all that does is to prevent a deletion. So if you were to update a row in a table or delete a row, somebody can't drop the table at the same time because you're holding that access share lock on the entire table as well as the row. And of course, once you finish, they can delete it, but while you're actually doing it, it would not be able to.
But I cannot see it.
You can't see it. So if I take a look at, let's go up to a delete example. So here's a delete example. And you see how I have a row exclusive lock on the table?
Okay,
so I
okay,
have an
okay,
even
okay.
more powerful lock.
It will be looks like a lock escalation. No?
It looks that way, but I see what you're saying. So you're saying if I do a select,
Yes.
then I have a share exclusive, and then if I'm advancing it to row exclusive, isn't that a problem? And surprisingly, it is not. It looks like a lock escalation, but effectively, I would be... So I already had... So what's happening, I have a lock that prevents the delete, okay? And now, when I make it more powerful, it's still preventing the delete. So it's not like I'm going up. Like you were prevented when I was down here, so when I go up to here, you still are prevented from dropping the table. So it doesn't work in the same, I know what you're saying. There isn't a lock escalation case where you typically drop a lock and then try and get a bigger one. But in this case, we're just uniformly increasing it. It doesn't cause a problem. Yeah. It's a good question, though.
Okay.
Thank you. I have this if I have a Russian question. I'm ready.
What we should do to avoid deadlock when we have many sessions and many users?
Right. So Postgres automatically detects deadlocks and will automatically terminate one of the sessions. The only way to avoid deadlocks is for people to lock things in the same order. So when you look at your applications, a lot of times what causes deadlocks is, let's suppose I'm going to lock two things. One application locks table 1 and then table 2. Another application locks table 2 and then table 1. So in the simplest way to avoid deadlocks is to go over your applications and try and make sure the locking happens in the same order in all of the applications. That's 80% or so of the problem, is typically people, all sorts of different people are writing applications, and if they're locking things in different orders, you can easily get into a deadlock case. If you lock them in the same order, you don't get into a deadlock case. Right there, yes.
Okay. Thanks for your talk. My questions probably doesn't regard. You talk about vacuum full. As I know, vacuum full performs reorder records in separate storage, remaining current records immutable. Why vacuum full taking access exclusive lock conflicts with read operations?
So that's a good question. So the reason is because with vacuum full, we're taking the table and we're making a brand new version of the table. And the table is going to be brand new. So we're going to make a brand new version. So the problem is that while we're doing that, we don't want people reading it because we need them to see the new table. So it gets into the gentleman's question about lock escalation. If we allowed people to read from it, then we wouldn't be able to move it and point people at the new one. We'd be having to wait for all the readers to finish. Right? So it's really a lock escalation thing. We just say we're just going to lock it at the beginning because we know at the end we're going to need an exclusive lock to move everyone to the new copy. So potentially we could allow that like we do with index concurrently, but it's much harder to do. But that's related to your question, lock escalation, yeah.
Is it possible to add locking timeout in Postgres. In Oracle, I can write select for update, wait, for example, 50 seconds. It was very good for application, but in Postgres, I have only not to wait at all or wait up to.
Yeah. You can set a lock timeout. You can also issue a no wait command that will fail if it can't get locked right away. So either one, lock timeout or the other, will allow you to avoid. It's not done at the syntax level. It's done as a variable in the server.
Sometimes it's not usable.
Can you open page 75? 75 page.
Oh, 75, okay. Yes.
My question is why both update processes is waiting 703?
Yes, that is an excellent question. So if we back up, you remember this slide? Okay. So at the time, I don't understand why Postgres does this, but at the time that 703 was created, it waited on 702, okay? And then when 704 and 705 appear, they don't seem to know what they're waiting on, right? There's nothing there. Because what Postgres does is when you can't get a lock, it just kind of says there's no point in processing you because you're behind somebody else, so we're just going to leave you there. It doesn't update it. What happened here is once 702 finished and 703 got its lock, the system went back and said, okay, now I've got two people who are both waiting. Let's update them and indicate who they're waiting for. Okay? So I don't know why Postgres does this. It has to do, there's a problem called thundering herd. It's probably not a Russian term. But what you don't want is you don't want to release a lock and have 20 people all wake up and all try and get the lock because there's no point. Okay? But what it's trying to do is when 703 finally gets the lock, the system goes back and says, you know, 703 is really the one these two are waiting on. And because they've both been waiting, we're going to queue them up next. And somebody new who comes along, maybe a 707, they're going to have a blank there. So I believe the reason it's done is to say, here, 702 is waiting on 703. Anyone who comes after them, they don't get a record in that field. Once the first person leaves, anybody who's been waiting gets a record, a marker, okay? So that I think that's done so that we process people in order. We keep them ordered properly. I think that's why. I've always looked at that as kind of odd because in this case we don't list it, and I think it's every time we grant a new lock, we go and see all the people who are waiting and we give them, we put them in the queue. And anyone new who comes, they're going to get in the queue only when the next person gets through. I believe that's why that's done. A very good eye. Thank you.
I think it's more logical when 705 is waiting for 704.
Yeah, so the problem is that you technically could wake up either of these. So I don't necessarily know that we're going to wake up one or the other. What happens, and the way the system works, do you see how it's 703 at the top? 703 has locked its own transaction ID. That's the way Postgres works. I'm sorry, I'm speaking quickly. 703 locks its own transaction ID, so anyone who wants to wait will wait on 703. Effectively, once 703 finishes, then new people, someone is woken up, but we don't necessarily know who that's going to be. And then later, we clear it up. But it's not clear actually who gets woken up. It could be any of those processes. Because we basically have the scheduler who says, okay, now you can wake up these processes, and we just pick one to wake up. So that's why they both have to be marked, because we may wake up, whichever, the issue is there's CPU affinity, so we might end up waking up the later one too, we don't know. And then once we wake up the later one, that will be updated to wait on the person who just got the lock, right? So we don't predefine who's going to be woken up and create a line, because the operating system may decide to bring in somebody earlier. Great, thank you.
На кофе-брейк я хочу сказать, что на Хабре.
So coffee break. I just want to say that on the Hubber you have the articles from Igor Rogov. They're very useful and very good, but of course this is a very complex topic.